Okay, so what I want to do today is to start actually talking about distributed computing. All the semester we have been building up to that point by introducing various concepts, starting from sequential execution, talking about C++. Then we talked about various ways of doing parallelization, various patterns of parallelization on shared memory systems. And today I want to start talking about distributed parallelism. How do we program these really giant machines that consist of thousands of nodes with millions of cores? And there are some specifics, and that's why it's worth dedicating essentially almost the rest of the semester to this. There will be an introductory lecture today. I will talk about more how to use HPX in that context. I would like to do a whole lecture on a couple of examples for real scientific applications. How can those be written by just applying different concepts, different patterns on how to do parallelism in distributed systems. And by the way, the last lecture, what I was thinking, I thought, hey, let's do something fun. And since Python is so important to everybody nowadays, I wanted to dedicate the last lecture to how do we integrate Python with C++. So how can we utilize what we've learned over the semester and make it available in the context of Python scripts in a very transparent and very nice way. So I hope that will be interesting to you. It's diverging a bit from the main topic of the course, but I think it is still very up to date, especially today where everybody is talking about Python and everybody's doing everything in Python and nobody thinks about where does the performance come from when you do Python, right? And if you look a bit deeper, all the performance in the Python scripting comes from C and C++ code that is behind the Python interface and is called directly. But I'll get to that later. Okay, so let's go back to where we started this course, where I looked at what is the scaling progression of modern CPUs today. If we start very early on, the first CPUs had essentially this structure. You had a fetch, decode, read, execute, write cycle that is executed constantly, where the execution focuses on the current instruction. And the instructions are being fetched from external memory, and each of those instructions reads and writes data to the main memory. This was a model used for, well, it's essentially still the very basic underlying model of all computing today. To an extent that this is called the von Neumann computing model. So it's very simple, and the CPU fetches and executes the instructions, and each of the instructions takes many cycles on the core. At that point, it worked very well because the clock rate of the CPU was comparable to the speed the memory could provide, the access speed. Cores evolved. The first thing that was added was kind of pipelining for the instructions, because people added more and more transistors to the silicon, and they wanted to speed up things. And in order to achieve more operations at the same time and higher throughput through the cores, there was some pipelining associated with it, where different stages in the execution loop were focusing on different instructions at the same time. Later, cores added reordering of those instructions if possible, or doing two instructions at the same time. If one of the instructions was focusing on integer arithmetic, for instance, the other one on floating point arithmetic, these could be performed at the same time during the same cycle. So the pipelining still fetches all the instructions from the memory, but this time more in a stream fashion. And it became apparent more and more that the trip to the memory was turning into a bottleneck, because the clock rates were increasing, and the pipelining allowed for many more memory operations that could be performed. And so this turned into a bottleneck here. but we know that story. It's really just a recapitulation of what we have seen in history. So in order to mitigate the clock speed differences of the cores and the external memory, people started to add caches to the cores, where there's an instruction cache, a data cache, and sometimes a shared cache between the two that allowed us to utilize temporal and local and spatial locality in order to decouple the core from the relatively slow external memory. So these caches are very fast. Well, still not as fast as the cores, but a factor of, well, n faster than the external memory. So kind of in between the clock rate the core provides and the clock rate of the external memory. Around 2005, people realized that, well, what they said, the free lunch is over. So it's not, at that time, when you needed more compute power, you just waited for Intel to give you a new CPU, which ran on twice the clock speed than before compared to the old one, and give you much more performance. The thing was that clock rates were plateauing off, and they were plateauing off mostly because the clock rate is has a quadratic dependency on the power required. And with power, well, comes great responsibility, obviously, but with power also comes a lot of heat. So higher clock rates created a lot of heat, and it was impossible to dissipate all that heat from these chips when the clock rate is very high. And you still see today that the clock rates, the highest clock rates we see in silicon CPUs is about 4 gigahertz. Nobody goes beyond that. Well, without water cooling and liquid cooling or putting ice cap on it or whatever, you know. There are people who overclock these things really heavily, but that's specialized hardware. So the way out of that dilemma was to, instead of having one core that runs faster, having two cores that run with half the clock rate. And that created other problems, because what we now need to do is we needed to add caches and made the caches between the cores coherent, because otherwise all the programs would break. Right? Nobody wanted to break existing code. So they created hardware that ensures that while we have separate caches, they are still consistent. So if one of the cores changed a value that happens to be in the cache of the other core, then the internal cache consistency protocols made sure that these values are the same. Even more cores, so that evolution is still going on today. We are today at, I don't know, 128, 256 cores per chip. So no surprises there. The cores share the slower memory externally, but have some cache consistency protocol that allows to ensure that the existing software still runs correctly. Silicon grew out of the desired real estate on the silicon grew so much that you couldn't place everything on a single chip anymore. So people started to say, okay, let's have several chips. Let's have several sockets on the motherboards and just place different identical chips on the same motherboard. And as we will see, these things have up to 4 of those nowadays on the high-performance computing resources, which immediately creates a problem. Hey, what do we do with the external memory? Is that external memory all connected equally? Or is that external memory non-uniformly connected to it? Will each of those sockets have its own external memory? Which is a matter of bandwidth, layout on the motherboard, and so on and so on. In the beginning, people tried to have a uniform shared memory that is connected to all the sockets uniformly, but very quickly it turned out that this is not feasible because it limits the bandwidth right? This memory block has a certain bandwidth it can provide, and if you connect too many cores, that bandwidth just limits us. And we have seen the effects on the roofline model while discussing the roofline model, that this is detrimental. So the next step was to actually have the same thing, multiple sockets on the same motherboard, but this time several memory buses. So each of those sockets has its own bank of memory and can access that memory directly, but there's still the possibility for the other cores to access the memory of the other socket, albeit with some additional timing overheads. But people usually ignore that overhead. But if you read the literature, you will, or Google just for NUMA, non-uniform memory access, you will see that there are certain things you have to take into account when you have to deal with these architectures, because you want to avoid cross-NUMA domain traffic. So while this core is able to access that memory over there, it takes a bit longer than accessing the memory that is directly connected to the cores. That aside, it's not really relevant for our discussions. I just want to give you the full picture of where things where things stand. So what's the next step? What we have seen so far is that people have tried to ensure coherency of the data inside one of those blades, inside one of those computers, essentially. So everything inside one computer relies on the coherency of the data access. So everybody sees the same data, and there is no problem with sharing data amongst the different cores. But if we go further and beyond one blade, put many of those blades in a common chassis, then we suddenly have the problem that we have separate memory spaces. So each of those blades has its own memory bank, its own address space, and there's no way for directly accessing data that is on the neighboring blade in the chassis. And things get even more problematic when you put many of those chassis in a rack, or put many racks in a center, or put many of those centers in the cloud. So there's no coherency anymore between the data that is stored on one of those blades with the data that is stored on the other blades. No automatic coherency. So we have to make sure that we find a way to program these things, which is very, very complicated. Well, once we're at that point, we got a supercomputer. Yeah, that's what we're aiming for. And that's just one of those things. You can think of the supercomputers as being a bunch of racks, usually in a room that has a size of a tennis court or larger. And well, they require a lot of energy, as we will see. But the problem is, how do we use these things? There, on the biggest supercomputer, publicly known supercomputer today, we have about 10,000 nodes, 10,000 blades. Do you connect 10,000 terminals to these 10,000 blades to program that thing or to start programs on the machine? It's not even possible to do it with virtual terminals, right? You don't want to open 10,000 windows just to work with that machine. So how do we do that? And what if I need even more power? Well, more cores, more blades, more chassis, more racks, more centers, well, and more nuclear power plants, right? That's the downside of all of this. And by the way, the AI revolution we are seeing today is one of the main energy-consuming things we have around. The latest numbers I have seen is that AI today in the world requires a sustained power supply of 50 gigawatts. 50 gigawatts. That's about half of the nuclear power plants the US has. So it's half of the nuclear power plants the US has is spent only on AI worldwide. And that is expected to grow exponentially over the next years. So AI is evil. And I'm very content because that power requirement of AI will ensure that we will know will not be able to use it for anything really bad because we will run out of energy before that happens, which is good. Anyway, just let's have a look at where we are today. There is a website which is called top500.org that gives us, which is updated twice a year with a list of the top 500 computers we have in the world. And if you look at the list, the most recent list that was updated in November, the most powerful machine is called El Capitan. It has 11 million cores, about 1 million cores, CPU cores, and about 10 million GPU cores. Energy requirements, 30 gigawatts. So they definitely have a nuclear power plant next to it in order to power that thing. And by the way, the 30 gigawatts are used, half of it was used to heat it up, and the other half of it is used to cool it down so that the damn thing doesn't melt. So that's the practice. But the interesting thing to note here is that it's a very interesting architecture where you have, normally you have GPUs and CPUs sitting on different ends of the system, and it's very difficult to transfer data from the CPU to the GPU. And if you talk to NVIDIA, they will tell you, yeah, it's very difficult because you always have to transmit data explicitly from one end of the memory to the other end. This is using AMD MI300 chips, and those chips have the cores and the GPU cores on the same silicon. So they share the same memory. Very nice architecture. I could talk about that machine on and on, but please Google it if you're interested in more details. About 10,000 nodes, as I said, 40,000 GPUs. Well, you get kind of the idea. The second one, about 9 million cores. The third one, Aurora, about 9 million cores. And the fourth one, about 2 million cores. So how do we program these things? Just think about Amdahl's law. Right? Amdahl's law tells us that if we don't parallelize our application 100%, we have a theoretical limit in scalability, where how much faster can we go with the same problem size. And if you want to be fully scaling on even only 2 million cores, you have to have a parallelization in your application that is unachievable. Right? Amdahl's law tells us that we have to have 10 to the minus 6 sequential code in our application, and the rest of it, 99.99999%, has to be parallelized, fully parallelized, in order to scale 2 million times on a particular problem. Not achievable. Now, I gave you the way out of that, which is Gustafson's law. Tells us that in order to use these machines, we don't try to run faster, we try to run bigger problems. I'll get back to that bigger problem issue in a second. Just to remind you, on this slide, I showed you that in the first lecture, where I said, okay, these are the technologies, the clusters are here, these are the paradigms, and we have talked about some of those paradigms during the semester. And I said in the beginning, well, all of this, you have to think differently about things. But what I want to do today is to give you the C++ approach, how we can do actually the programming on the cluster. If you look at it from the distance, you will realize, well, all of those, we don't have a giant parallel computer, essentially. What we have is a large amount of normal computers, which could be parallelized a bit, but there's not one single computer that has 2 million cores. That doesn't work. But each of those separate computers have their own memory, independent. They have their own storage. They have their own operating system running. The only thing is they are connected using high-speed networking. And high-speed networking, well, if you remember your operating system class, they probably will have told you that in order to do networking, you have to use a different interface compared to when you do normal programming. You can't just address use a pointer and access arbitrary memory, you have to use sockets or similar networking interfaces to do that. So it requires different paradigms. We want to find a way to unify all of that and to get to a point where we actually can program these machines. At the same time, there are no parallel programs that run on 2 million cores, obviously, right? It's just a bunch of programs that run at the same time on the different nodes. And each of those programs has its own memory, has its own storage, operates on its own operating system. And that's important to understand. So each of those nodes runs its own program, runs its own executable. I will show that graph over and over again today, but let's simplify things and say, okay, I have two nodes that are connected with a network. So you have one node which has working of its own instructions and works with its own data. And now you need the data that's actually on the neighboring node. What do you do? Well, as I said, you can't do that because it's not the same address space. There's no memory bus going from here to here. Well, people have implemented things on top of networking, which is called RDMA, Remote Direct Memory Access. And there are systems that allow you to address arbitrary bytes in the system across the whole machine. But again, the latencies are even another order of magnitude, if not 2 orders of magnitude higher compared to local external memory. So if caches have a latency of about, 20 nanoseconds, local DRAM has access times of about 100 nanoseconds. RDMA, remote direct memory access over the network, when you want to read a byte from a different node, takes about a microsecond. So it's something that is not feasible if you want to do that on a large scale. So what do? We said the remote memory is not directly accessible. So we need to explicitly copy things from one node to another. Each of those computers, each of those CPUs has its own memory, has its own instruction stream, has its own data, and works on its own. But whenever they need to communicate, they have to use the interconnect between those, and I will get to that in a moment. So all of this begs a couple of questions. If you want to program that kind of system where we have tens of thousands of these nodes or millions of cores, should all nodes do the same thing at the same time? Should they? Should they not? Will there be a speed up if they do? Will there be a speed up if they don't? As we add more CPUs, we have to make the problem bigger. And that's what I meant was when I was referring to Gustafson's law. It's the only way to actually achieve more performance if we have these large machines. We can't use strong scaling that relies on Amdahl's law to scale out to the full machine. We have to rely on Gustafson's law, which is weak scaling. In other words, when we add more nodes to our program, to our application, we have to make the problem bigger. So we can't make things faster, but we can make things bigger. Very US-style way of doing things, by the way, in my opinion. Can we keep all the data on every node if we keep making the problem bigger? Well, probably not. If you think about these really big simulation systems where you simulate, galaxies with billions of stars, or where you simulate the weather forecasting, where you want to forecast storm surge when a hurricane comes close to the coast. That amount of data that has to be held doesn't fit into a single node anymore. Even if you have hundreds of gigabytes of memory available on each of the nodes, it doesn't fit in there anymore. So the answer is probably no. So we have to find a way to not only make the problem bigger, but we have to find a way to split the data in a way that we can still reason about it and can still work with it. So do we need all the data on one node? That's the other question. Probably not. And I will show you some examples why that is. We actually don't need everything. In the simplest case, if you're simulating a galaxy on 4 nodes, you could just split the galaxy into 4 pieces and handle each of the 4 quadrants of that galaxy on a different node and just manage the boundary regions between those in a certain way. So we don't need to have all the data on every node. So that saves our life. So what do we keep? What don't we keep? Let's assume that every node has some of the data, but the union of it should be all of the data. There might be some overlaps, as we will see soon, next lecture perhaps, but overall it should be collectively exhaustive. So all the data should be somewhere. Otherwise we can't solve the problem, which is kind of obvious. Okay, data, we have kind of decided. We said, okay, we can split the data into pieces. We should be able to make the problem larger by having more nodes, by splitting the data into smaller pieces. That should work. What about the program? Does the program grow with the problem size? Does it matter whether I have a galaxy with 100 stars or a galaxy with 1,000,000 stars? Probably not, because, well, the physics are the same, right? It's just gravity, you're calculating forces, you're calculating directions, how the stars move, and that logic is the same, most likely for all physics-based problems. So the program probably doesn't grow with the problem size. And if you think about it, you probably need all of the program everywhere anyway, because even if you're solving a physical simulation problem on one which is split across nodes, you have to do the same work on all nodes anyway. So yeah, we probably will not split the programs into smaller pieces. We probably will have the same code running on all the nodes at the same time. Okay, anybody knows that lady? Ever heard of her? It's a Greek lady, became famous here in the US, Frederica Darema. She was famous probably before you were born, so it's not surprising that you don't know her. What she has done, she has published a paper that came up with a way to coordinate all of that, to create programs, a conceptual approach to how do we do these kind of things. And she defined it as single program multiple data, SPMD. We talked about SPMD in the context of data parallelism, but there it was more SIMD oriented, that you had a lockstep between the processes that do the same thing at the same time. SPMD is more of a concept that allows for the processes to run independently and have certain synchronization points in between that allows them to coordinate their actions. As it turns out, SPMD is the most widely used model in distributed computing today. And we will go back to that over and over again, even if the way they have used it in Fortran might not be the most modern or interesting way anymore. And we will see how we can extend and build upon it. Okay, so SPMD means you have several processes, plates, each with its own memory, and you will run the same single program that runs on all the cores at the same time, on all nodes. But you have multiple data in the sense that the data is not the same across all the nodes. So each of the nodes has its own piece of the data, but uses the same code to operate on that. So how do you pronounce SPMD, right? Well, people usually say SPMD. I don't know if that's the right way to do that, but let's call it SPMD. As I said, it's the most widely used model in distributed computing today. It's a much better model than what we defined based on the Flint's taxonomy when it comes to distributed computing, which is exactly what I said. You have the same code, you have different data on the different nodes in the running at the same time. So every node runs a sequential process. Well, and that's where things get a bit uncertain today, because today it's most likely not a sequential process anymore. It's most likely a parallel process itself. If you're from the Fortran community, and there are still, you won't believe it, but there are many people who like Fortran, which is, by the way, one of the first programming languages developed in the 1950s. What they do, they use SPMD for their parallelization. And by the way, Los Alamos, for instance, right? They have millions of lines of Fortran code that they use to manage the nuclear stockpile of the US. And believe me, nobody dares to even look at that code, not even touching it, because they say, okay, don't touch it. And that's a big problem, because Fortran can't, or it's very difficult to make Fortran multi-threaded. So the model they usually use, they run not one program, one process per node, but they run one process per core on the node. So if you have 128 cores, you run the same process 128 times on the same physical machine. And that avoids the multi-threading issues, because each of those processes is single-threaded. But originally, people were talking about sequential processes, where all of the code is replicated. Essentially, all nodes run the same executable, the very same executable. The data is distributed using some resource allocation scheme, but the problem here is that the data dependencies are probably not disjoint. So you might have dependencies from one node to another node. So those dependencies we talked about last time when we talked about tasking might have cross-node character. And this is kind of a problem, because you can't directly access that data, right? So the data may be needed by another node, but can't be directly accessed because it's partitioned. But still, all the partitions kind of give you the union of the whole program.
Can you explain the
Yes.
dependency? In the previous slide, the data dependency, this is a big problem.
Yeah, it's a big problem.
Yeah, it's a big
Well,
problem.
well, go back to the galaxy problem, right? You have the galaxy, you want to split it into two nodes. One half of the galaxy is on one node, the other half is the galaxy is handled by the other node. What happens when one of the stars moves across the boundary between those two? So will you move that responsibility for that star from one node to the other node? You still have to compute all forces between each of the pairs of stars in the system, right? So you have to compute the forces between the stars that are on different nodes as well. So there are dependencies in the computing which go across the node, and you have to somehow handle those. Doesn't make sense? Yeah? No? You're nodding.
The big problem is able to get them back.
Well, you have to. Well, let's go back to n-body problems, right? The galaxy. What does it mean? If you want to simulate a n-body system with many stars, you do it time-step wise. You look at the current velocities of the stars, what direction do they go, and the current positions of the stars. And then you compute the gravitational forces between each pair of the stars.
Okay.
Sum the forces up, and that gives you the force that acts on each of the stars separately, right, which allows you to find out where will the star move in the next second or so. Yeah, like moleculars or stars, or it's all the same. Yeah, and once you have computed the forces, you compute the next position after a certain delta t. You say, okay, I'm looking at it every second or so. So I compute where will be the star in a second, and then you repeat the process. Okay. Do that over and over again. It's kind of a time-step loop, if you want. And but to compute the forces, you have to compute the force between each pair of stars. And if the stars are distributed across the system, that one node contains a large array of the data for one half of the galaxy, and the other node contains the data for all the other stars, then you have to compute the forces anyway, even if one end of that gravitational relationship is on one node and the other end is on the other node. So you have a data dependency there that you have to somehow resolve. Yeah? Does it make sense? And that is ubiquitous. So it's not just in these n-body simulations. You have that everywhere. Just whenever you split data into pieces, you might have cross dependencies between the pieces. Yeah, okay. Okay, so we figured out we have a sequential process running here. Let's call it sequential for now. And we have a sequential process running here. And this process needs to access, or no, this process needs to access data from this memory. How do we do that? Well, the only way we can do it is to somehow go onto the network, go over the network, go on this side until one of those cores, please give me that data I'm actually needing. So you have to somehow tell the other guy, well, you have to tell your brother, please go get some beer, right? That's essentially the idea here. You're too lazy to get your beer yourself, you tell somebody else to get the beer for you. And this is what's happening. So there has to be some network communication going on in order to either fetch that data or to instruct the other node to do something or this kind of thing in order to establish these connections between the nodes. And that allows us to go back to that scheme that everybody is doing its own thing. But there might be some communication going on between the two nodes over time as needed. And this is kind of the scheme that is applied for these distributed computing systems. Another person, anybody? You definitely have heard that name. I understand if you haven't heard the name of Tony Ware. So it's Sir Charles Anthony Richard Ware, or CAR Tony Ware, a very famous person, one of the first people who got the Turing Award in 1980. He came up with that dining philosopher problem, by the way. You might have heard of that. It's a classical problem that describes deadlock situation, how to resolve those. So he's one of those guys. And he has created an axiomatic basis for reasoning about computing. So you know, axioms is kind of the basic thing you use in math. So a set of predefined rules that put together allow you to build your whole reasoning about something. And he has done that for computing, and he has used that axiomatic basis to define a schematic or very formal way to describe essentially SPMD. How do these things operate, and what axiomatic basis is needed for that? And he called it communicating sequential processes. So it's a sequential process. Again, we will kind of weaken that. Nowadays, especially with HPX, it's a very parallel process. But the point is that there are processes that somehow talk to each other. And what he has proven, or he has proven that applying this scheme will give you the correct results, essentially. So it's mathematically proven. By the way, it's pronounced CSP. Whenever you hear anybody talking about Ps or CSPs, it's probably communicating sequential processes. Read about that person. Very, very widely educated person, and he has done a lot for the theory of computation. Okay. Enough of pretext. So I just wanted to give you a longer introduction into what is distributed computing today and how it's done. And I want to give you an example. And for that, I just want to go back to our trusty example we had, computing pi. And just for you, if you don't remember, and I don't blame you if you don't, you can compute pi by computing the integral, essentially the area below that function, which is defined as 1 over 1 plus x squared. And if you take the integral in the interval from 0 to 1, you get exactly pi. So we have done that with threads by saying, okay, if I want to have that area, why don't split that area in rectangles where the rectangles, the width of the rectangles can go towards 0. And the closer we get to 0 in terms of the width of those rectangles, the more accurate we can approximate our area, which is essentially this formula. Or if you think about it in an iterative way, pi is roughly the sum over all the areas of those rectangles. And each of the rectangles is h, which is the width, times the height, which is essentially the term on the right side of our summation. We talked about that extensively, so I'm not going to explain that. What we also said is, okay, this is simple code. Here we go. Just a loop going over all the rectangles, computing the area of each of those rectangles and summing them up. We went through that. I want to do it again just because the angle is slightly different to what we have done so far. How do we parallelize this problem? How do we go from a problem we want to solve and maybe know how to solve sequentially to a parallel program that actually scales, that actually gives us better performance than sequential program? Because why do we parallelize things? We want to run faster or we want to run bigger. So let's look at it from the standpoint of SPMD, of SPMD. We have to find a way to decompose a problem into pieces that can execute in the SPMD model. So we have to distribute the data. We can do it by task or by data. Let's do it by data here. So, and we have to manage the communication, the sharing of the data somehow. We have to decide on a fundamental organizing principle. Should we build it around data composition? Should we build it around task, data flow? Today I will focus on the data composition part. In other lectures I will probably talk about tasks or data flow schemes to do that decomposition, that organization principle. We will use SPMD as a programming paradigms, and we will manage processes and their communication, and we will introduce a concept which is called collective operations that allow us to manage that synchronization between the sequential processes that run. Okay, so that's our function. We said, okay, addition is commutative and associative, so why not split that problem into 4 problems? It doesn't matter in what sequence we compute that integral. It doesn't matter in what sequence we compute all these rectangles. We will always hopefully get the same result. Well, normally. So instead of computing one big sum, we compute 4 sums when we split it into 4 pieces, and we still should be able to get pi. So we have the same code. We run it 4 times. We have run it from 0 to n over 4, from n over 4 to n half, from half to 3/4, and for the rest of it. It's all what we have discussed, so I'm kind of skimming over things and just to save some time. But just to give you the idea and to remind you where we actually have been. But if you look a bit closer, hey, we have the same program and we have different data, because what's different is the n. The begin and end is different. So is it SPMD? I think we can apply our SPMD scheme here, because SPMD means we have the same program, but we kind of divide our data into pieces. When we did it initially, we said, okay, we have 4 loops, so why not run these 4 loops sequentially and let each of those loops do one of the sums? But that doesn't give us parallelism, so we went to the scheme of using threads and run each of those pieces on a separate thread. Right? We have a pi helper function which does a computation from begin to end, and we launch that function on 4 threads, join with those threads, and in the end we should get pi magically somehow. And we discussed that in detail, so again I'm skimming over things. So we created 4 tasks, where each of those tasks runs on a separate thread, and each thread is responsible for one of those sub-parts of our integral. Now, how do we get to processes? We have the same problem. How do we make processes out of that? Well, if you have one process, and one process probably calculates one of those pieces, right? It's a main which has its own computation, its own output, and we have that 4 times. For each of those processes, the only difference is, again, the boundaries of our iteration. So how do we get from here to there? And that's where the magic happens. Because what we want to do, we want to have 4 programs that all look the same, but all do different things. Again, you will notice that the difference between those 4 programs is really just the iteration boundaries, right?
Then why do you need a data flow?
Hmm?
And why do you need a data flow?
I don't need data flow here. We will talk about data flow in other places, but here we don't need it. We just split it. Yeah, it's all parallel, sure. They run in parallel. There's no dependency, at least not yet, right? We need to collect the result, the overall result in the end somehow. We will see how that works. Okay, so what we have is 4 nodes and 4 programs that run at the same time on the different nodes. Each of those programs runs on a different compute node in the system, and they are somehow connected over a network, and they might communicate. That's the other part. So they will have to do some communication in order to achieve what they want, and we will discuss that in a moment. Okay, so how do we get from here to here? Or another problem. Let's look at that again. And if you think about it, we see that all 4 threads share the n, right? So that n is the same for all of the threads. There is no need for us to do explicit sharing because n is local to one process. All threads read the same n. N is exactly equivalent to the sequential n, obviously. And because n is at the same memory location for all of them. So all the tasks we had use the same n and the same h and the same pi. It's the same variable. There's no need to do any sharing, any communication. It's just magically there. So, but if you look at processes, you will notice that each process has its own n in memory. So these are distinct variables. Every n is local to its own process. And while all programs are identical, they need to use the same value of n, otherwise things will not work. No process can directly read or write n from the other process. So this is not possible. So what do we do? How do we get the right value for n to the other processes? Well, obviously we somehow need to copy things over, and that's what we will do. We decide that one process actually will define n, and all the other processes will receive those values as copies. While threads have the same value, processes are reading copies of n. And that's a very important notion, because what distributed computing does, it relies on a as-if equality. Just by assuming it's the same value, so you can write code as if it was the same variable. And that is what these SPMD models rely on. You distribute the data across a system, and then you write code as if it was the same variable, because you know that you copied the value of that variable. So everybody is working with its own copy, which is as if they were working with the same one. And that means we have to make n consistent across all processes, otherwise it will not be as if. I think that makes sense. Okay, so that's where we started. We have a single program, but what about multiple data? If we want to have multiple data, we have to modify our code slightly and have a different begin and end in our actual program, and then somehow initialize begin and end appropriately depending on what process I'm running on. So if this is not really SPMD, this is code that begins to be resembling SPMD, because it's really the same code if I somehow manage to get begin and end appropriately initialized here. Then I have the same code running on all nodes. Absolutely same executable, right? I compile it once, I get an executable, I run it on all of them, and I will get what I want. So begin and end has to be different. Again, the question, how do we do that? Well, apparently we have to do something additionally. So we need a different begin and end for each of the processes, and we can achieve that by saying, okay, we could get n from the command line first, because n has to come from somewhere. But should we get n from all command lines? Probably not. You don't want to type 10,000 command lines with an n on it, right? That's something which is, you you probably don't want to do. So it's better to get it at one node and send it around to the others. So you have to pass it on one command line only. And since we want to have a single program, we have to let every process attempt to get n from the command line. And if it's there, it uses it. If not, then it receives n from another process. That's why I'm just checking whether there's something on the command line, right? If argc is larger than 1, then actually try to get n from the command line. Otherwise, don't do that. But that still doesn't solve our issue with begin and end. So how do we do that? In order to do that, we need a means to distinguish the processes. So all processes need to be able to distinguish themselves from all other processes. And this is done by assigning a number between 0 and p to each of the processes, where p is a number of processes, and that allows for each of the processes to query the system, say, hey, what is my p? Who am I? And that number will go from 0 to p. And then once we have that, we can use that number to actually modify our code such that we can compute begin and end based on n and our p. So let's look at our code again. This is our initial program. We set n to a billion. This is computing pi. And in the end, we print pi. We've seen that code last lecture when I talked about HPX a bit. I showed you, hey, there's a way to find out how many localities, how many p's do I have in my application, how many processes do I have, which is the getNum localities function. And there is a function which tells you my p, get my locality ID, which is exactly what we want. So if the locality is 0, we get it from the command line, and only there, because we know that only locality 0 will receive it on the command line. The rest will not get it. Then we can compute the block size, which is n over the num localities, because that tells us how many iterations do I have to do locally, which is, well, let's assume it divides evenly n over the number of processes involved. And that allows us to compute begin and end by just saying, okay, block size times my locality ID and block size times locality ID plus 1, which gives me the iteration boundaries. And then we have begin and end, and we can do our computation, which exactly looks the same on all nodes. And in the end, we want to print it on one of the localities only, right? This is where we print pi. What's missing? Well, we need to send n to all the others. That's one thing, because otherwise the other localities might have a different n. And we need to somehow collect all the partial sums we had computed on all the localities back to locality 0 so that we can get to the overall pi. Okay? And that is where collective operations come in, because that is what happens in these two places is a collective operation, because it involves all of the localities. They will communicate with each other. In this case, there is a so-called broadcast operation where you give a single value to everybody. And this is probably a reduction operation where you just collect all the values from everybody and reduce it afterwards using just addition or something like that. So let's have a look at that in more detail. By the way, anybody knows that guy? You know him? Okay. Anybody else? This is Mr. C++ Graph, the author of the Boost Graph library, one of the most erudite people in the graph computing, Andrew Lumsden, good friend of mine. He came up with a better name for all of that. He said, okay, SIMD, SPMD doesn't sound right. I need my own abbreviation. I need to be famous, right? I need to come up with something that everybody will remember me. And he said, okay, why don't call it distinguished replicated processes with distributed data? Or because he likes these acronyms, he called it DROP-D. Not drop dead, DROP-D, okay? By the way, if you want to meet him, and we can arrange that. He's still around. He's about my age, so we can talk to him. Just as a side note, I said Mr. C++ graph theory. You probably have heard of the Hungarian mathematician Erdos, who is well known for his graph analysis work in math. And that person is very famous not only because of his work, but because he had thousands of collaborators. So he's well known in the world of collaboration. And people have come up with a so-called Erdos number. And the Erdos number is how far removed are you from Erdos in terms of publications. So if you had a publication with Erdos, you have an Erdos number of 1. And if you have an Erdos number of 2, you know somebody, you wrote a publication with somebody who wrote a publication with Erdos. His Erdos number is 4. So my Erdos number is 5, because I have written a publication with him. So if you want to have a Erdos number of 6, just write a publication with me, and that makes you famous, okay? Just as a side note. Okay, collective operations. We assume that the process with a locality ID 0 receives n from the command line. The process sends it to all others, and this operation is called broadcast. Well, broadcast for a reason, right? You're shouting, you're telling everybody what you want to know. And in HPX, this is very simple. You do broadcast. I'll say a word about the communicator in a minute, and you pass the thing you want to broadcast, n. On the locality 0, n will be used as value, and on all other localities, n will be set to whatever was received. So it's a reference. Broadcast will receive the value and will initialize your n with whatever it has received. We will talk about communicators next lecture a bit more extensively, but for now, think about communicators as the set of localities that are involved in a operation, in a collective operation. It kind of represents all localities that participate in that broadcast operation. Okay? Then every process calculates its own begin and end based on its locality ID. I showed the code. Every process computes its part of the overall solution. And then we have to reduce the result. And that again is a collective operation, which is called reduce. You give it the same communicator because the same set of processes is involved. You pass your partial pi to it, and on locality 0, it will receive the sum of all of them because the operator you specified is std plus. So it's a very simple way to do these collective operations by just calling one function and another function to first distribute the value and then get all the values back. And that means that our code I showed you now turns into this, right? So instead of the comments, I just have these 2 collective operations in there. And you see that the rest is very much the same. And the beauty of this is that it's really the same code, the same executable that runs on all localities. And it will do the right thing, and it will coordinate amongst all the localities that are connected. And it doesn't even care how many processes you run collectively, right? You can run 1,000 processes, the code will work. You can run 10 processes, the code will work. Well, except for that division operation, which might give you the wrong results if it's not dividing evenly. But I just wanted to skip that problem here to make the code more readable. So always assume that n is divisible evenly by the number of localities. Otherwise, you will get wrong results. That's it. There you go. Single program, multiple data in a very simple way. I know it's kind of unusual because you have to think about being in 2 places at the same time. You have to think about, okay, this code is running here, this code is running here, all do the same thing, but in the end they should do different things. How do I achieve that? What do I have to make happen in my code in order for this to work? And what we will see in the future is that this scheme is absolutely ubiquitous. So almost all distributed applications work based on that very scheme. Yes?
Does this snippet include the communication from the receiving end?
Sure. Reduce. So broadcast this is a reference. It will take the value from locality 0 and will give it to everybody else. This takes a reference as well, but only locality 0 will receive the reduction result. By default, we will see that you can specify other localities, but by default it uses locality 0 for that purpose. So it's very, very simple in the end. It's just not a reduction operation in the sense we have seen it in the data parallel sense where everything is on the same node, but that reduction takes every single value from a different node and does the collective reduction afterwards. Okay? Okay, so where are we? Every process has independent memory space. The code is replicated. The data is partitioned. And the union of the partitions gives you the whole problem. Well, assuming that n is divisible evenly by num locality. Otherwise, we have to kind of be careful on the last of the localities because we might have less data in the remaining piece. But that aside. So we started off with this. We had the decomposition into pieces. We went to threads where we were sharing n. From there, we went to the processes. I showed you what transformations we had to do in order to do that. And eventually, we got to the point where we had 4 nodes, and each of the nodes runs exactly the same code. And okay, I left out the communication operations here, the broadcast and the reduce, but those are the ones that actually communicate over the network and do the appropriate operations. So this is a complete program when you use HPX. Again, in the beginning, we get the number, our locality ID, and the number of attached processes. We get n from the command line. We share n over the wire with all others. We do our local computation. We do the reduction in the end, and locality 0 collects all partials and sums them up. And on locality 0, we print our desired result, because only there we need it. You don't want to have it printed 10,000 times on your terminal, right? You need it once. So you want to print the result only once. The takeaway message is, this pattern is ubiquitous. So whenever you do distributed computing, try to think about it in these terms of some initialization that does all the magic depending on how many processes you have. Then you do the actual work, and then you share the results and reduce the results and collect them in one of the places and do whatever you want to do with it. Write it to a file, write it to a terminal, and so on and so on. So, any questions? Okay, then I'll let you go. Thanks for your attention. Last administrative announcement on Thursday. Next lecture will be given by Professor Koppelman. I asked him to give you an introduction into using CUDA for GPU computing, and he is happy to do that. So I really hope that you will be here so that he has some auditorium for that. And we will resume after the spring break, 2 weeks from today. Okay? Thank you so much.